I'll just add a couple of brief words on that, but again, this is meant to be a discussion period, so hopefully we can pretty quickly get into discussion on how to choose the right parameters for what you're doing. The goal of this particular session is to really discuss the pros and cons of choosing the various measurements that are possible for, that are appropriate for your experimental design. So I hope that you'll kind of think about the types of experiments that you want to do, and perhaps we can have an open discussion of let us know what you think you're thinking of measuring, and we can discuss the pros and cons of that. But before we get into that, I just wanted to touch on a few things, and Andrew already covered a few of these, but I feel a need just to re-emphasize in a slightly different words perhaps, but something you've heard many times: precision is not the same as accuracy, right? So the precision is the ability of a measurement to be consistently reproduced. Accuracy is essentially the confidence that you have that that measurement is correct, and those two are not the same. And just to kind of illustrate with the target type design, so these bullets here are quite accurate, quite precise. They're very close together, but they're not very accurate. They miss the bullseye. Conversely, if you take the average of all these, they're quite accurate. They're very close to the bullseye on average, but the precision is not as good. They're farther apart. You need to think about what is most appropriate for your application, and you can't necessarily say, well, this particular approach maybe isn't as good, but it's okay. If the accuracy is off, then you could be getting the wrong answer, and that's not necessarily okay. If this is the case where it's just not as precise, but the accuracy is still right, then you might be okay. But if you have some combination of this, I mean, there are other versions of this, right? You can have Andrew suggested there might be another target that's just completely blank, where all your shots are not even hitting the target. Another way of looking at the work that Andrew just presented, these are some figures that Rick Wanenkoff put together that I thought were quite interesting, and there's a couple of them here, is to think about the processes that you're trying to understand and what the different measurements might be able to tell you. And these are just three examples that Rick kind of picked out looking at. So first we're going to look at the PCO2 on the y-axis and the dissolved inorganic carbon on the x here. And if you've got some perturbation that you're trying to understand, what are the processes controlling that? And this is your starting point. The red box here shows the uncertainty as Rick estimated them for these particular measurements. The green line would be the increase in DIC in an example where you just had CO2 diffusing into this sample. So you're increasing the CO2, and so that obviously affects both the PCO2 and the DIC and gives you this sort of relationship. The black line is where you're starting here, but you've just dissolved calcium carbonate into solution. Again, it affects both the PCO2 and the dissolved inorganic carbon and gives you a trend like this. The blue line is a combination of dissolution and respiration such that it ultimately gives you an equivalent change of DIC and alkalinity. So there's some ratio of the respiration to. So here you see you've got a fair bit of spread. If you were doing this pair of measurements, you would hopefully be able to distinguish between these different processes that are changing the values. Here we are. In this case, you've got PCO2 and total alkalinity. for the same sort of processes. So here you're just adding CO2 to the system. In that case, of course, you don't change the total alkalinity, but you do increase the PCO2, obviously. Dissolution changes the alkalinity and the PCO2, and here's the combination of respiration. And you can go through and you can do this for all the different measurements. Here's the one that really stands out, as Andrew pointed out with the uncertainty of the calculations. I think this really illustrates it very well. PCO2 and pH strongly covary. They're controlled by nearly the same processes. So when you start to look at the effects of adding CO2 versus dissolving carbonate versus some combination of respiration, and all of these tend to fall along the same line. So if you're moving up and down in this way, how do you know what's really controlling it? Obviously these have vectors that go in the opposite direction too. So if you see a decrease along this path, is it carbonate dissolution, or are you just degassing, losing CO2? If you're moving along this direction, are you precipitating calcium carbonate, or are you absorbing CO2, or do you have respiration going on? So you need to think about what pair will allow you, if you're interested in understanding the processes that are going on in a situation where you can have multiple different processes affecting the results, are you making the measurements that can actually distinguish between those? And finally, the last thing was, I just was sitting last night, since we had a bit of an early night, and thought I would try and do at least a qualitative, and we can argue over but this was just to get something down on paper that we can discuss, a qualitative assessment of the different parameters. And I started off thinking in terms of discrete samples. And so this was just, again, my personal biased view on how difficult is it to make a discrete DIC relative to alkalinity, pH, and PCO2. Again, very qualitative, and this is my personal bias. The cost of making those discrete measurements for DIC, alkalinity, and so forth. How long can you store the samples? We've discussed this kind of over the time that, pH is a great parameter to measure, but you can't store that for months and months. You couldn't collect a pH sample and send it to Andrew to analyze for you. And again, we can argue over the exact values for these numbers, but I think the relative numbers are probably close.
Well, the real difference there is that because of the concerning sample handling for pH and PCO2, those numbers reflect the fact that you're not poisoning the samples, for pH particularly.
Right. And related to that is this idea that we discussed the first morning of whether the parameters are temperature and pressure dependent or not. Right? So the nice thing, particularly if you're collecting samples from the ocean interior where you've got lower temperatures and higher pressures, is that the DIC and alkalinity have that advantage that they're not affected by those. And I gave the example of the PCO2 from the CO2 cis calculation. We looked at the PCO2 sample from the deep Pacific in situ is about 600 microatmospheres, but by the time you warm it up and measure it on the ship, you're measuring something that's 1,350 microatmospheres. So you then have to go back and try and correct it back down and do a 50% correction back down to in situ conditions. And there, as Andrew just explained, there's a fair bit of uncertainty associated with doing that, particularly if the PCO2 is higher than 500, right? So there are issues with that. But then, so all that was kind of based on the discrete measurements, and then I got to think, well, in some cases, discrete measurements don't even work for some measurements. So what can we do continuously? And there you start to get into, now there are certain parameters that you can do easily that are more available than others. So I just came up with two. One is whether you can do continuous measurements. I would say right now that the DIC and alkalinity can be done continuously, more or less, but it's completely in a research mode, that there are particular researchers that have developed techniques to do that. This is not something...
Automated sampling, it's not that you get a continuous alkalinity.
Right, right. It's sequential, frequent, discrete samples, but it's done automatically in a way that looks more or less continuous. But again, these have only been done by individual investigators that have put a lot of time and effort. It's not something that you could say, oh, you know, just let me buy one of those.
Chris, for continuous, do you mean something that could be deployed, say, for an underway sampling system on a vessel?
On a vessel, yeah. As opposed to something you would put on a buoy, which is the next thing. pH and PCO2 are commercially available in some form or another. For moored DIC, this would be something that's completely autonomous, not necessarily on a buoy, but on a platform or whatever, but something that you would just set up and leave all on its own. The DIC and alkalinity, I would argue, are still in development. There are a few people that claim to have instruments like that. I think they're not ready for prime time by any means, but lots of people are working on those. The pH and the PCO2 are commercially available, and Thursday morning I'll be showing you just an example of one of those for the PCO2. So anyway, I just kind of throw that out for what it's worth. Again, we can debate. But so now to start the discussion, I just wanted to kind of prime this with a few questions that you should be asking yourself. You should be saying, you know, things like, do I need continuous readings, or can I store the samples for later? That has a big impact on the instrumentation that you need. You know, if Jean-Pierre needs to have a controller that needs that immediate feedback of what's the pH so I know whether to add acid or not, it obviously doesn't help him to collect discrete samples and analyze them a day or a week or a month later. You got to have that continuous measurement. What processes are you trying to characterize? That was my earlier thing, looking at the different pairs and tell you different things about what processes. And if you go back to that kind of tertiary diagram that I showed you, the reason why we have good commercial instruments, autonomous instruments for measuring PCO2 is because for many years we've been trying to understand the air-sea exchange of CO2. The best parameter, if you want to do that, is to measure PCO2 directly. So a lot of time and effort has been spent on developing that particular set of instrumentation. The concerns over ocean acidification have been fairly new, and so this idea of we need autonomous instruments to measure DIC or alkalinity has not gotten as much attention or funding. What are the master variables? You know, again, this is a similar sort of thing. If I'm trying to understand PCO2 gas or CO2 gas exchange, I should measure the thing that most directly addresses what I want to know. Or if you're controlling the CO2 in a laboratory experiment and you're going to be showing later the response of the organisms to different levels of CO2, you might consider, well, maybe I should measure CO2 directly. Because again, any calculation is going to have some uncertainty associated with it. But you have to weigh the issues of, can I measure PCO2 better than I can calculate it? How important are precision and accuracy? That's been mentioned a number of times. Do the measurements need to be autonomous, or can someone, do you pay someone to oversee it? This is from what Andrew said this morning. The number one thing that he listed as for quality of the measurements was the training of the person. If you have a more autonomous instrument, perhaps you don't need to invest as much in having someone trained to be able to handle those samples. And then consider the cost of buying the instruments versus sending the samples out for analyses. We talked about that a little bit. So at this point, I'd like to open it up for discussion, people's thoughts. Don't everyone speak at once?
That's a very important discussion, and I think it's very critical that we provide clear messages to the audience, and what you have said is just very good, and also what Andrew addressed. I have a few comments. The first one, obviously, is the central lab is not practicable for perturbation studies, because you want to have access to the data right away, not next Monday, but the next hour, perhaps sometimes instantly. So it could be useful for quality assurance, if you take samples and you store them and then subsequently you send them to a sample lab and to make sure that you're doing things relatively okay. The propagation of errors, Andrew, we discussed it in clean, and I think it would be quite easy to implement in softwares that exist like CCAR. I'm prepared to do it. I mean, if you provide me with the way to do the calculations.
One formula.
Yeah, one formula, but yeah, there is more than that,
Yeah, I know. That's why these things don't exist.
Okay, so that can be done. An important point that you raised is where do we need to constrain the carbonate chemistry for perturbation experiments? Perhaps a good starting point is to look at the chapter by Jim Barry in the guide for best practices. And Jim, in this chapter, recommends several options, and he says if you can do two levels of carbonate chemistry, then you should use this PSU2 level and this one. If you can do 3 levels, then we suggest this one, and up to 8. And in the worst case, the PCO2 levels are 100 microatmospheres apart. So that would be a good starting point to decide how well we need to know the PCO2. I would say that plus or minus 10 microatmospheres is good for perturbation experiment purposes.
So
what's that?
10 microatmospheres at 1,000 total is 1%. That's probably a factor of 3 better than you could hope to do it.
Okay, so that's good. But 1,000 is really at the far end of the range, I think, that is recommended by Jim. I mean, most of the data from the levels is suggesting now between 280 and 800 or 850, like that before.
So when is this guide? The guide's not available yet, is it?
Not yet, but as I said yesterday, you can download the almost final versions on the EPOCA website.
Is there? When do you expect it to be completely finalized? And
we hope to get it published early 2010. But 40 authors, some of them don't respond very fast, so bear with us. And the last point is the uncertainty that Andrew described. Perhaps I missed this, but how do you combine the precision and the accuracy into a single number? Did you elaborate this?
I did not develop that discussion. That would have taken a lot longer. Essentially, if you know your measurement is wrong by a certain amount for a certain reason, you fix that reason. So what you end up with are uncertainties that are affecting the accuracy, bias, that you don't have full control over. And what happens then is you say that they must be within a certain range because of the kinds of experiments you've done to show that. Having decided they're in a range, you can say, well, that range would be 4 standard deviations. So you can treat it as a standard deviation, which is then propagated through the calculations in the same way. And so that's how it's done. It's assuming that if you have a known bias for a known reason, you fixed it. you buy a volumetric flask, your manufacturer doesn't say this is 1 litre at 20 degrees centigrade. They say it's in the British units, it used to be a class A tolerance. It's 1 litre plus or minus something. So you already have an estimate of what the contribution. Every time you use that flask, you will be the same amount wrong. This is the confusing part. It's not random. But to put it into the formula, the sort of international community has agreed that this way makes sense and comes up with uncertainties that are at once calculable and meaningful for making decisions. Are they good enough or not?
You also have to remember that uncertainty and accuracy also frequently are a function of the concentration of whatever you're measuring. You know, it's great to have the reference materials, or, you know, a lot of people standardize to the reference materials, but that's one point. So you may be quite accurate at that particular concentration, but you're not necessarily accurate at another concentration. So what sort of, can we talk about maybe some other types of experiments or monitoring or ocean acidification type things that people are wanting to do, and what they're thinking about measuring and why, and what their thoughts?
All right, so I have a question that's based on how you choose which parameters you really want to follow an experiment that has biological organisms in it, because an earlier statement when we were learning about total alkalinity pointed out that microorganisms may produce organic acids that will change your total alkalinity. So you probably don't want to use that as one of your parameters to constrain the carbonate system. So if you were doing a perturbation experiment where you wanted to know how the carbonate system was changing, but you had organisms in it, how best do you go about monitoring that? Because there's also issues with pH in terms of the two different methods in which one will give you an accurate measurement you can use. So I guess my question is, if you're trying to do that sort of experiment, I mean, other than buying a DIC analyzer and PCO2 equipment or collaborating with someone, what is the best way to go about doing that? And I guess it goes back to the question of how, if you're doing major perturbations where you're comparing 3 very different CO2 treatments, how close can you get with measuring pH, total alkalinity, when you've got biological organisms messing things up?
Let me tell a story. There's a paper in the literature where people measured at 2 CO2 levels, and they quote those CO2 levels as being a factor of about 2 apart. One they say was 380, the other they said was 760. They put organisms in it. They also measured pH with electrodes. The difference in hydrogen ion concentration that they measured for their 2 systems was equivalent to about 15%. It should have been closer to 90% for that 0.88 factor I had on the board. So clearly they didn't have what they thought they had for the CO2 levels. A whole lot of this discussion is you have to have a way of saying, yes, I do have what I expected. And in my, coming back to your answer, no matter how much we have scared you about pH, I still stand by what I said earlier this morning, which is that the total pH hydrogen ion concentration measured spectrophotometrically can probably be done day in and day out after some practice and with some equipment with about 0.01 in pH. That's 2.5% in hydrogen ion concentration. That was the error I was assuming in my propagation calculations. So I really think that has a lot of advantages. Total carbon, I think in any system where you've got a lot of contamination increased uncertainty in your ability to interpret alkalinity, you've got to bite that bullet. You have to measure total carbon. It's a whole new game. It's quite expensive to buy. You've got to practice. But you probably have to do it. That's my own personal opinion on these things. Alkalinity, if you've got systems where you can interpret alkalinity measurements, it's Chris's chart here. It's more moderate difficulty and a lower cost. PCO2, he's got these markers very high, and they stay quite high.
Yeah, measuring discrete PCO2 is very difficult.
So I would recommend pH and total carbon for many things, but there is no doubt that there's a lot of systems for which an alkalinity change is a geochemically or biologically interpretable parameter. And as Chris said, if you want to measure and look at a change in something you can measure, why not measure it? Why calculate it? And so these are the trade-offs.
Yeah, one thing I noticed that isn't on the list is if you're attempting to interpret carbonic acid system from any of these parameters, all of them are temperature and salinity dependent. And so perhaps you might want to talk a little bit about the uncertainty that's contributed by salinity measurements, which are conductivity based. And I know that amongst the ships, the intake temperatures that they're reporting are oftentimes not comparable between the ships. And there's a fair amount of error that's associated with temperature. And how does that uncertainty contribute to our interpretations? Even if we get these right, just the basic observations of temperature and salinity, how does that contribute to the uncertainty? Because it's something to worry about.
Yeah. My comment to that would be that temperature is the one you have to worry about most. Because the pH is temperature dependent. The PCO2 is temperature dependent. You want to make sure you know what temperature you actually measured it at. You want to make sure you know what temperature you really wanted the result at. That means both thermometers have to be properly calibrated.
What's the acceptable uncertainty for temperature measurement?
You have the same problem I said there, that you can do a partial derivative of the change in this with respect to temperature. I said for PCO2, it changes 4.25% per degree Celsius. So if you only want it within 5%, let's go for 0.3 of a degree, 1/3 better, so that it leaves room for other errors. But 5% is quite big for many people. If they were looking at air-sea PCO2 exchange, they certainly don't want it to 5%. They want it much better than that. They're looking to try and get it to meaningfully better than 1/10 of a degree Celsius. So it depends upon your need, how well. Salinity, in the simplistic view of did I measure it well enough, probably doesn't matter. For most things, 1/10 in salinity is not going to be your biggest problem.
For the
Clearly, if you're in an estuary where 10 in salinity is a possibility, then you've got to worry about this. And I have limited experience. One thing I would point out to people that bear in mind when you're doing spectrophotometric measurements with samples that vary in salinity, much of what you get from a background measurement is a measure of the refractive properties of your liquid. And as you change salinity, the refractive index changes. And so you want a background at the salinity that you're actually making the measurement to get reliable data.
Also along those same lines, though, just to follow up on it, you mentioned borate. We mentioned borate whenever we discuss alkalinity, and then we don't ever discuss the analytical methods to determine it, whether we should or shouldn't. We largely oftentimes ignore it in the blue ocean, but in the coastal systems, is this something we should be worried about, and should we know how to make those measurements as well, or do we just always mention those in theoretical discussions but never actually address them?
For boron, traditionally, the boron to salinity ratio that is used, that says that in 35 salinity there'd be about 420 micromoles of boron, was done in the 1970s and seemed plausible. more recently, Kitek Lee has reevaluated the method and done a paper showing how you could do that method more reliably and suggests that that number should change a small amount. That paper is in review at the moment. This is a small amount that would affect on the edges of what we're doing with open ocean work. Up an estuary, I rather suspect it depends upon the geology of the drainage basin. The one estuary that I have ever made boron measurements on, it was proportional to the conductivity salinity all the way. It was as though the freshwater had almost none in it. But that's the Tamar estuary and one nice, colourful, pretty part of southwest England. I have no statement to make on any other estuary in the world.
So, Andrew, in my conversations with other seawater chemists, they've advised that overdetermination of the carbonate system would be desirable. And if I understood you correctly, you suggested that measuring more than two variables is not necessarily desirable. So can you comment on that?
Of course. I would first say that for many people, PCO2 is not going to be one of the variables you measure on for discrete samples. If you're in a ship doing underway measurements, you get that, and it's a good measurement. And then overdetermining is trivial because you wanted to do two normally on discrete samples. If you were to do pH, alkalinity, and total carbon on all your samples, you would get extra information. One thing you would get is a better understanding of the overall uncertainty of what you were measuring. The cost is you'd have to have either more people, so each of them had the skills, or a more skilled person that would surely be asking you for more money after a while, who could run all three of these well. And it would take more time to treat each sample. And so the trade-off is the added value of getting information about your uncertainty. In particular, it gives you information about whether there are contributions to alkalinity from organic acids and how big a problem that might be. But you have to have the quality control system for every one of these methods working well to use them together. So the workload goes up as well, and that's the trade-off. That are you gaining enough extra information for what is at least 50% more work, but it's actually more than that because you're not only going to do the work of analyzing, you're actually going to do the work of looking at it.
Right. I mean, so we do this in the open ocean where we feel we understand the system fairly well, and we're doing state-of-the-art measurements. For coastal measurements or a lot of the type of experiments that you guys are probably thinking about, I would say the biggest problem is, okay, say you do make three measurements and they don't agree. How do you attribute those differences? It could be measurement errors in any one of the things that you did. It could be organic acids for affecting alkalinity. It could be the salinity differences affecting the pH. It could be, I mean, it would be very difficult to, it does give you a sense of the uncertainty. In some ways, though, you may not really want to know just how uncertain your measurements really are, because that'll really discourage you. I think we...
Actually, if you set up your lab and you have the ability to measure all four parameters, you could see which ones of the four is out, and if three are agreeing quite closely, you know where your problems are lying. So, I mean...
Yes, over-determining the system in the lab could be useful, where you can constrain the variables as well as possible.
Those of you that do analytical measurements regularly, in the quiet of your own mind, ask yourselves how many you throw out as lousy measurements. If that number is significantly lower than 3%, then these comparisons will probably be useful to you. If it's higher than that, you're always going to be trapped in the, oh my God, was this one of those lousy data points? And so you have to have the measurements running at a reliable level of quality before before over-determining gives you anything?
I actually have two questions, because I'm gonna be working with phytoplankton, and we're growing large volumes of them, because we're also gonna look at whether or not their lipid and fatty acid compositions change internally, because there's evidence that they're made. So, there's some issues I've gotta work around. And one of the ones that I had mentioned briefly that I'm wondering is a valid way to do it is we're gonna have to filter, because we're gonna have very dense cultures. Can we get around some of these issues by, since we also will know that we have, that when we're dealing with procolithophores and stuff, that we're gonna have, that as an issue. Can we take particulate DIC and, samples and run them through an elemental analyzer and then try to back correct for some of that? Because if we don't filter, we have issues. If we do filter, we have issues. We can measure particulate DIC at the lab. We've done that for years. We're sure about that.
Yeah, sure. Like I was saying yesterday, I guess, you've got, there are no perfect solutions to these, and you've got to evaluate the potential uncertainties of either. But you've got two separate measurements now that you're having to use one measurement that has some uncertainties associated with it to correct another. If you go through the propagation of the errors.
It's the same problem we had here. If that background is got a large uncertainty associated with it, it doesn't matter if it's small. It does matter if it's big.
Is it one way, though, to check to see how larger, like if I get two numbers that are completely different, that may tell me that I'm either sampling wrong or something?
If you've done enough other work to be confident that getting two numbers that are completely different is an unusual occasion, then you can go ahead and do that. You first got to get to the situation where you know that you don't get numbers that are different. Having got that, then you can start saying, okay, I'm looking at this and I can see this. It might work sensibly for many of these things. I suspect you could filter adequately effectively. One could discuss, and probably the thing that really would need testing is whether it's desirable to poison and filter or filter and poison.
Yeah, okay. And my second question is, I don't see a way of doing it, but because I'll be doing algal cell cultures, I'll have to measure phosphate and silica, so they have an uncertainty that will also add to the equation when we do the calculation of everything, correct? Okay. But when I do something like phosphate and silica, because we're also doing it in estuaries with different salinity ranges, I usually use the method of standard additions to take care of that matrix effect. I don't see that being helpful for trying to do it for DIC or alkalinity. I can't see a way of doing the method of standard additions.
Yeah, you're very fortunate with DIC that the method is acidify and measure how much CO2 there was there. That's substantially done that way, matrix independent. So it's not going to depend on what the salinity background is. It may depend on how much CO2 there is in the sample. That is, if you put my reference material in and it's 2,000 micromoles per kilogram, and your sample is really 1,000 micromoles per kilogram, you don't know for sure that yours really is doing quite as well as it was at 2,000. And you might want to think about how you check that. But DIC, total carbon measurements, these ones, dissolved in mayhem, they are substantially matrix independent. For alkalinity, they're somewhat matrix independent, but the problem is if you switch salinities drastically back and forward in the cell, it doesn't work as well as if it stayed at constant salinity, doing constant salinity samples. So the uncertainty will increase if you're always running a variety of salinities in your something that allows you to address that. The beauty there is if you want an alkalinity for a sample that's at 16 salinity, take our reference material and dilute it with deionized water. Alkalinity won't matter for that sample handling. You can do that test. You can get alkalinities at different levels and different salinities. Changing the alkalinity and the salinity independently is more complicated.
Yeah, I would just temper that a little bit by stating that carbon is everywhere, right? So if you do a standard addition type, and you can do a standard addition type experiment with alkalinity, but even DI water we find frequently has a measurable blank of alkalinity, and any water that you've got is going to have CO2 in it. So you just need to be aware of that.
Yeah. Our experience has been that DI water that actually has that around about 18 megohm resistance does not have any alkalinity in it. But the moment you're careless enough to put it into a container where it washes the walls a little bit, or add salt to it that you thought was pure, you will find extra alkalinity there.
Right. Okay.
I have one question for the calibration. So how often should we calibrate the instrument for these four parameters?
I'm sorry, I missed that question.
He asked how often we should calibrate. And unfortunately, this is related to how long a piece of string is. As long as you want. Because what it really requires is that if you were measuring the same sample over and over, you might conceivably get a line like that. More likely, these would be horrendously scattered around that line. So that really it's you would have to calibrate often enough that when that line starts to appear out of the scatter you're willing to accept, you've already recalibrated. That's different for every design of apparatus. For our alkalinity instrument, we calibrate it twice a year, once a year. We test it every 10 samples. For total carbon, we calibrate it each day's lot of running as an average of sample calibrations done during that run. For a pH electrode, you might get good data if you spent all your time calibrating. So it really depends on when the change in calibration factor would come outside the uncertainty range that you're getting and that you're prepared to expect. And you want to calibrate probably 2/3 of the way along that line. And finding that out, somebody can say always calibrate every hour. And that's probably only reliable if you didn't really need to calibrate until 2 or 3 hours. If you really, an hour was the limit, chances are sometimes that wouldn't have been good enough. So you have to find this out, sadly, the hard way, by running the same sample a number of times and saying, God damn, I'm sure the calibration's changed. So I should have calibrated it sooner. Next time I'll do better. But there's a trade-off. Every time you calibrate, that's a sample you didn't run. But it's a group of samples you had better confidence in.
Don't you love answers like that?
I have a question regarding cultures and another one regarding menstrual samples, and this is related to phytoplankton. There are some cultures that simply do not grow when you start bubbling them. In situations like that, can you prescribe something else besides just field bubbling?
Next week.
Yeah,
This
that's,
area is covered later in the course,
But-
and I'm not sure whether they're doing it, but yes, you can. There are ways to manipulate CO2 chemistry without bubbling. I'm sure Jean-Pierre will talk about it. If he doesn't cover all the ones I'm thinking of, I'll butt in at that time.
I mean, you can do things, you can bubble it and externally and then run the water through, and there are things you can do.
The second question deals with adaptation and acclimation that we spoke about when we first talked. Yesterday we saw some experiments where natural samples are taken and, at any given concentration of CO2, and then you ramp up the CO2 to a certain, say 800 or 750, and then you make measurements of various things that you think are going to be affected. And I'm not sure whether that's the right way to do it, or we should be really thinking about a slow process of adaptation. Because when you have a system that is perturbed so much, how reliable are the answers that you hope to get?
You're thinking in terms of the chemistry or the biology?
Both in terms of the chemistry and the biology. It could affect so many other things if you alter the pH, for instance, so much.
The chemistry changes its properties almost instantaneously. The slowest is the gas exchange, and you can manipulate that to be quite quick. As a result, the section we're talking about here, how do you understand the chemistry, no matter how much you've said, oh my God, that's ugly, this is the easy bit. You raise exactly the things I'm sure people are going to talk about for the next week and a half, about concern about design of experiments for ocean acidification. But in terms of the chemistry, we're home free. It's relatively straightforward. We know how to do it. You just pay your money and practice.
I would just add that we really don't know about the biology, and that's why a lot of us are here. I was just going to say, I would argue we really don't know about the biology. We have a lot of discussions about short-term versus long-term experiments and whether or not particular organisms are able to adapt to slow changes versus rapid changes. And I really think we haven't run enough of both kinds of experiments to know exactly who's capable of adapting over what time frames. But Andrew's right, the chemistry is the simple part of it. Biology is why we're all here learning this, so we can spend the years that it's going to take to figure that out.
Chip. Run, Mary, run.
Just throw it like football.
Can you speak further on the work that was done to establish the storage sample times and how worried I should be about samples that may be stored longer than what you've listed there? Specifically speaking, I mean, that a DIC sample is traditionally, my vision is that it's the anchor measurement, and I could be out to sea for longer than 3 months, not capable of breaking that.
I think that these numbers that Chris has here are sensible, but by no means hard and fast. The way these numbers are arrived at, and really about the only way you can get a hint of this, is you take lots of duplicate samples, and then you have two options. You either have a method that you can analyze it reliably today and in 6 months' time, and know that you would get the same answer if it were the same sample. That's not been done as often as you would hope. More typically, those two samples are then analyzed 3 months later, or maybe 6 months later, or maybe 12 months later, and the degree to which they diverge is a hint that all was not well. And the assumption is being made that they're not going up together at the same amount or going down together at the same amount. but differing amounts, and after a certain amount of time you can see that that difference has grown. The Keeling laboratory at Scripps collects duplicate samples every time and analyzes them, often many months later. In that case, which is open ocean water, these are very conservative estimates. 12 to 24 months often shows no difference. But the word often is not always.
Right. So these numbers are based on my experience with running samples, and it's kind of the difference between what Andrew showed earlier of, state-of-the-art laboratory accuracy and precision was significantly better than in the field, or we had state-of-the-art on a ship, and then he had the other. This is what I would put into the other category. We have people that send us samples, from all around the world, and frequently they end up taking months to get to us, or we take months to get to analyzing them. These are people that are not necessarily trained experts at collecting the samples. That, I went back yesterday and was looking at some of the grease seals from the samples that you collected the day before. Some of them were great. Others had very clear channels that where the gas could be exchanging through the bottle. Some of them had the right size headspace, others didn't, and the warming of the bottle kind of popped out the top a little bit. This is a recognition that sample handling is very important and frequently is not ideal. And so yes, these are somewhat conservative numbers. Andrew says his CRMs are good for years and years and years, but he also very carefully filters them, very carefully prepares the bottles, very carefully poisons them to make sure that they're preserved. These are numbers that I'm comfortable with, that the average person collecting a sample and sending them to me, following my 2-page sampling protocol, or what's in there. Keeling, I would point out, does store his sampler, but he also has about a 10-page sampling protocol with a lot of very detailed instructions on exactly, you do this at this time.
One other aspect, just to point out for people, that if you're going to store samples for total alkalinity, it has to be Pyrex glass. I said this before, I'd say it again. No matter how well you did everything else, if you stored them in the bottles we sampled into the other day, 6 months later, those would be obviously different for an alkalinity sample.
That being said, as I think Andrew mentioned, we think, it's hard to tell because the results, you can't even predict how they're going to change when they go bad. The one thing that does seem to be consistent is if you have duplicates, and I always recommend collecting duplicates, that they the measurements always get noisier. It's not like they're all going to change by exactly 10 micromoles. They're going to get noisier. So in a sense, we find that we can use the noise and the variability in the measurements compared to what we expect as a sense of perhaps how good the samples are.
And this is an important piece, which is to remember that what you want is the uncertainty of your measurement process. And that includes collecting and storing the sample until you actually got to measure it.
It's a good question.
I'm hoping you can comment on some of the general logistics in designing some of these experiments. Obviously, we're interested in CO2 as the variable, but most of our organisms need oxygen to live, and we need access to them as researchers to manipulate systems. So maybe you can comment on open versus closed systems especially given all the hand-wringing we've done the last couple of days about bubbles in a hose and then having a tank that we've acidified, but it's open to the atmosphere. Are we going to be running into problems, big problems in that way?
Go ahead.
What you have here is you've got a somewhat slow process, gas exchange across a reasonably quiescent interface. So you get advantage out of that. As temperature changes, those things, it's going to suck CO2 in and out. I mean, the same thing, just warming and cooling will do that. So if you have a system that you're not exchanging the water and you're not actively controlling the CO2 concentrations, my estimate, and I'm sure this will be discussed more later this week, is that you are at real risk that you do not have an adequately controlled experiment. But if you're making efforts in those regards, the extra benefit from sealing it all off from access may not be sufficiently big to counteract the obvious disadvantages.
And you're absolutely right. So I just, my little story of someone that I know that tried to do a ocean acidification perturbation experiment, decided to cut some corners, and was, rather than pay for a CO2 in air standard, just got a CO2 in nitrogen standard, bubbled it through their tanks, and all their organisms died. Oh, ocean acidification. No, you suffocated them because you bubble out all the oxygen. I'm sure you'll hear about this, you know, what to do and what not to do over the next week.
We're going to talk more about this tomorrow, so this is where volume of your system plays a big role. And also looking at background information and gathering as much information as you can on the organisms that you're working and what their typical rates of metabolism are, designing that experiment appropriately with respect to volume, control of that system, and what reasonable fluctuations are for what you're testing. So we'll talk about more of that tomorrow.
In light of this little brief discussion and your comment earlier about one of the papers that had obvious inconsistencies in their interpretation of their carbonate chemistry, from a chemist's perspective, could you, may not be fair, but could you put a percentage on the number of perturbation experiments that you think adequately constrain their carbon chemistry that are in the literature?
The number that I think constrain it as well as they claim is quite small. But adequate is the discussion we haven't yet had. And so I hesitate to do that.
So I guess maybe another way to pose the question would be, in trying to interpret the biological responses that we see in the literature and the inconsistencies that already appear in biological responses, how much of that is related to our inability to properly control our carbon chemistry, as opposed to real biological responses?
I would doubt that that's a major contributor given how organismal variability alone is so ostentatiously a part of this. But the paper I particularly pointed at, it clearly was. They said such and such, there's no real calcification change. And my answer would be, yeah, they were in the same solution.
Right.
Within 15%. So maybe 15% is the number.
And it's not just CO2 chemistry, it's all the rest of the chemistry too. You got different nutrients, you got different, all kinds of things that...
Yeah, our point here is not that this is the most important part of your lives, but that this is the part you can fix. Leaving time and effort to do the hard bit.
I would also add that sometimes it's not a matter of adequate control so much as adequately knowing what the ranges were and whether or not those ranges were within reasonable bounds, reasonable numbers. So sometimes you can't necessarily control.
But you can at least document.
But you can at least document and know whether or not you're within reasonable ranges.
Deborah? Great. Oh, sorry.
I wanted to go back to Marcus' point about the oxygen and in relation to this recent comment. And we, more often than not, do not take into account the diel cycle. So we look at, you know, the light cycle, and we ignore the fact that some of the key enzymes have a dual function, have a carboxylation function and an oxygenation function. So instead of looking at, if we think about continuous culturing approaches and the fact that we want to, keep things really constant, we need to look at ranges and how these values vary over the light-dark cycle. And I think that's something that we are not really thinking about. And another thing about the oxygen is that yes, it doesn't have any impact on inorganic carbonic chemistry, but if you think about, not in the case of populate, of course, which are marine beasts, but in other organisms, the oxidation of organic matter will result in CO2 production. So how, whether we want to take that into account in some, benthic systems, it really needs consideration, I think.
So, Andrew, you pointed out the importance of storing your samples in Pyrex containers for certain analyses. Or in regards to an earlier question about closed versus open systems, some of the biological experiments that we do, or I do at least, can be run in a closed vial for a particular period of time if there's a little bit of headspace. But what I have no understanding of is the permeability of some of the plastics or the glass that we might use to contain the biological experiment. Do you have any information about how that might affect our results?
Not enough. We've looked at using plastic bottles to store CO2 samples, and it clearly is not a great idea. And I haven't yet found a plastic where I wouldn't use that phrase to describe it. So most of these are permeable to some extent. We've even tried the plastics that are designed to be oxygen impermeable, because those are the ones designed largely for the food industry. And CO2 is not oxygen. It gets through smaller holes. Maybe it has to go through lengthways, but it clearly does. It goes into these plastics. It may come out the other side, who knows. But we don't know enough about this. It's not been rigorously looked at. Once it was obvious it was not suitable for storing samples, we didn't ask which one would be the best if you had to put up with this. We just went back to glass and said, my next trial is aluminum with a plastic liner.
So we've thought about this a bit for our PCO2 systems, not necessarily for bottles, but for plastic tubing, different types of tubing. And there is information on the web that at least gives you a sense that there's over 1,000, there's 3 orders of magnitude difference between some plastics in their permeability to CO2, and that information is available on the web. Now that doesn't tell you that those plastics that claim to be very low permeability are impermeable. Nothing is that we've found is impermeable, but you can at least look on the web and get some preliminary, and I don't recall which is which. I could contact my technicians and get that, but there are definitely certain plastics that you absolutely don't want to use compared to others. So I think, how long are we supposed to go?
Just 2 minutes.
Yeah. So why don't we go ahead and wrap it up for lunch, and we'll see you back here at 1.
I will be here and Chris too. Chris, I think you're leaving on Friday?
Yeah, Friday
I'm leaving
evening.
on Saturday. So if you've got questions, you'll recognize us, talk to us.